is having a periodicity capital T, then what does Fourier series say? That if you have any periodic function having periodicity, say capital T in one dimension, we are talking of one dimensional case as of now, then we can write down that periodic function as a sum of sinusoidal functions. Like, I mean, it has the right hand side on this equation has two sort of terms. One are cosine terms, other are sine terms. So this is how any periodic function, I repeat, any periodic function can be written as a sum of sinusoidal functions which are periodic themselves. Now you should notice one thing here on the right hand side, that what is the periodicity of these sinusoidal functions? If you check, say, sine of kx, sorry, sine of k omega naught into t, where k here is any integer going from 1 all the way to infinity. So let us take sine of let us take sine of 1 into omega t, omega naught t. Let us take k to be equal to 1. Then what will be the periodicity? And let us assume that omega naught is nothing but 2 pi by capital T. Then what will be the periodicity of this function? Sine of omega naught T with omega naught equal to 2 pi by capital T. I'm asking you to find out what will be the periodicity of this function. Yes, any one of you, please try. I mean, all of you try in the notebook. Then let me know what will be the periodicity. Okay, so it will be T, correct? I hope all of you will be able to do this. How we will find out the periodicity? We have to actually replace small t with, say, t plus, let us say, we don't know what is the periodicity. So let us say it is, say, A. Then we have to replace it with the, like, what will be the periodicity? It will be the value of t for which f of t plus a is equal to f of t again. So I'm sure you all can work out this, and periodicity for this function will come out to be T. Interesting thing is that, okay, what we had assumed is, let us assume that the function f of these sinusoidal terms on the right hand side means if you have a periodic function with the periodicity capital T, then this can be written as the sum of sinusoidal functions of periodicities T and, okay, that was the periodicity for sine of omega naught t. What about periodicity for sine of 2 omega naught t? Suppose we take k equal to 2. Then what will be the periodicity for sine of 2 omega naught t? Suppose we take k equal to 2 here. Then what will be the periodicity in that case? Now I am asking, let us assume we are taking k is equal to 2. So in this case, what will be the periodicity? T by 2. Is it so? Are you sure? Yes, others, please check. Yes, correct. So periodicity in this case will be T by 2. Similarly, if we take k is equal to 3, the periodicity will be T by 3. If k is 4, periodicity will be T by 4. So the interesting thing is that any function which is periodic with periodicity T can be written as sum of periodic functions which are sinusoidal. Now, what is the difference between ft and this sine of omega naught t? The difference is that this is very simple, well-defined function, and ft in itself. So what we are actually trying here is that we are taking a function of any arbitrary shape, but having a periodicity T, and we are trying to represent it with the help of some well-known functions of well-defined shape. And how are the periodicities of those functions defined? So the condition is that the periodicity of all these sinusoidal functions should be either equal to the periodicity of the function itself, which we are going to represent, or periodicity of the unknown function, let's say f of t, and uh, 1 by n, where n is an integer, times the periodicity of the function itself. Or in terms of frequency, let us define omega naught as what we call the fundamental frequency. Then how we can obtain any periodic function of a frequency omega naught? It can actually be obtained from sinusoidal functions of frequencies. So here we can say what will be the frequency for sine omega t? It will be omega naught. Frequency for sine 2 omega t, 2 omega naught t will be 2 omega naught, and so on. So means by adding the sinusoidal functions of frequencies omega naught to omega naught, we can obtain omega naught, 3 omega naught, and so on. We can get any function with Fourier series, where this first term is called cosine Fourier series, and second term here is called sinusoidal Fourier series. So now it depends upon what kind of function we are dealing with. We may have either only cosine Fourier series, or we may have only sinusoidal component of the Fourier series, or you may have both. So for example, when you were doing Fourier series, you would have seen that if we have a even function, means f of minus t is equal to f of t, then the cosine Fourier series will only be there. And if we have an odd function, then we will have only sinusoidal Fourier series. If we have any general function, you may have both sinusoidal and cosine Fourier series contributions. And where these AKs and BKs are called Fourier coefficients. And how we can obtain the Fourier coefficients? They can be obtained with the help of these expressions. So you have done this. So I'm not going into details of this. Okay. Oh, now since all of you are online and the class has begun, so I would request you to mark your attendance. Just type your roll number in the chat box. Meanwhile, let us continue with the content itself. So now the question is, what is the relation of this Fourier series with the reciprocal lattice, which we are going to discuss? Well, so okay, let me, but that is what our reciprocal lattice. And instead of t, which was time in our previous slide, now we are saying, okay, it is periodic in space, say r. So the Fourier series can equally well represent the periodic functions in time, like sound waves or other functions which may be repeating with time. And it can also represent the functions which are repeating in space. For example, in any crystalline material, the atoms are repeating in space after some specific distance that we may call the periodicity. Now let us first assume a simple one-dimensional crystal, which is shown here in this figure. Okay, which is shown here in this figure. Now, this figure is trying to represent a hypothetical crystal, and rather than saying it as a crystal, let us say we are trying to represent the electron density inside a crystal. Now, since the atoms are periodically arranged in a crystal, so will be the electrons in a crystal, right? Because electrons are associated with the atoms. So the electrons or the electron density in a crystal will also be periodic, having the same periodicity as that of the atomic periodicity. Fine. Now, what we are trying to see here is that let us assume we have a one-dimensional crystal for which the interatomic separation is given by A, and the shape or the distribution of electron density is some arbitrary type of shape. So nx, these bars are trying to represent the shape of the electron density in the crystal. So if we have, so now this electron density in a crystal can be seen to be like a periodic function repeating after a periodicity of A, correct? So if this is so, then what we can do, we can use Fourier series to represent such kind of periodic function. So what is the periodicity here is 2 pi by, sorry, what is the periodicity here is A, correct? So what will be the corresponding Fourier series for electron density? So, okay, what is the periodicity condition is that, okay, n plus n of r plus t is equal to n of r, where capital T, this is something interesting you should notice here for three-dimensional case. For three-dimensional case, what is capital T is the lattice translation vector. What is lattice translation vector? That n1a plus n2b plus n3c, right? So what does this vector say in case of three-dimensional crystal? It just tells us that, okay, how the lattice points can repeat in the three-dimensional space, or what is the periodicity of lattice points in the three-dimensional space. So for one-dimensional case, this T is going to be quite simple, and it will be looking like, okay, 1a, 2a, 3a, it is like n times a. The translation vector will be n times a, because, okay, if you have a lattice point here, say at this point, then you will have a lattice point here after a distance a, then a lattice point here after a distance 2a and 3a and so on. So in one dimension, it is fairly simple. I think any one of you has unmute their mic, which is causing some disturbance at my end. So please mute your mics unless you have to ask question or have to answer something. Okay, is this clear till now? Whatever I am trying to say. So this is periodicity of electron density. Means electron density is having a periodicity A. Is this clear? Any question from the discussion till now? Yes. Am I audible there?
Yes, sir.
So is everything clear to everyone?
Yes, sir.
Okay, for Ankush it is okay. Means for others, I hope it is also okay. Fine. So if this is so, then what can we do for one-dimensional case? So now periodicity is A. So what will be the corresponding Fourier series for one-dimensional case? What was omega naught here? 2 pi by t, right? Now capital T is replaced by A, the periodicity. So what will be the Fourier series accordingly? Fourier series will be n naught, the constant term, and p being an integer, of course, greater than 0. Cp, this is cosine Fourier coefficient, cos of 2 pi. Uh, so instead of small t, we are representing small x here, means the variable is x, because our function is repeating in the space, not time. So we are saying, okay, the variable is capital small x, fine. So 2 pi by a, which is nothing but omega naught, as here, what was omega naught? 2 pi by t. So now what will be omega naught here? 2 pi by a, we will say. Rather, we don't say it as omega naught, but we say it as k, the reciprocal lattice vector. So that is from where that reciprocal lattice vector starts to come into picture. I will relate real and reciprocal lattice now shortly. So, okay, this will give you 2 pi by a into x into p, the same way. I mean, this was k omega naught t, this is omega naught, so this is one and the same thing. So So this plus there will be a sinusoidal term sitting here. Again, somebody has not mute their mic. Please make sure your mics are mute. Okay. So so now here is an important message that if you have a periodic function in one dimension having periodicity a, there will be a corresponding Fourier series which is written according to this. So now these Fourier coefficients Cp and Sp actually depends upon what is the detailed distribution of electron density within each cell, like each unit cell. Here in unit cell is of size A. So for example, I hope you remember when you were doing Fourier, you were finding Fourier coefficients for square wave, then the Fourier coefficients were looking of some specific shape. If you take Fourier coefficient corresponding to some other distributions, say triangular wave, sawtooth wave, the Fourier coefficients are going to look a different way. Same thing, I mean, these Fourier coefficients, what do they tell you practically is the detailed nature of the distribution of the function in the unit cell, how the function is varying inside the unit cell. So once you know how is the function in unit cell, of course it is going to repeat itself as such in the neighboring unit cell. So these functions, Fourier coefficients, actually decides the shape of the function in the unit cell. And what does these terms in the Fourier series say, like 1 omega naught, 2 omega naught, 3 omega naught, what does they tell? They tells us about periodicity, means after what length or after what periodicity the function will repeat itself, right? Because what is omega naught related to? It was related to the t periodicity, because omega naught, let me show again here, omega naught is 2 pi by t, so it is related to the periodicity of the function itself. So in same way, if the function is repeating after a distance a in real space, this is what we can call the real space, then after what values the terms will appear here in the Fourier series on the right hand side, means what value of this, what you can say, the frequency of these cosine functions or sine functions be appearing in the Fourier series on the right hand side. I repeat, what values of the frequencies will appear in the Fourier series on right hand side. So there will be 1 corresponding to 0, which refers to this constant term. Then there will be one term appearing at when p is 1, that will be at 2 pi by a. This one we are representing. Then we are representing 4 pi by a. Then we will be getting 6 pi by a. Then we will be getting 8 pi by a, and so on. Correct? So similarly, now, okay, we are saying, okay, we have negative terms as well. So I'm skipping that part, but yes, you should have done it in your earlier classes, that Fourier series, instead of writing here, the condition is that p is positive, means the integer, it is just a positive integer. Then we can write down this in this manner. Or negative terms, what we are trying to say is that one of the, or the cosine terms can be represented with positive values here, sine terms may be written as negative values here. Or if we represent it with the help of exponential form of Fourier series, then this restriction that p is positive will be lifted, and what you will be getting is that p can be any integer going from minus infinity to plus infinity. So that is the important thing, that okay, what all terms will appear in the Fourier series corresponding to the real space periodicity of a. The terms will be 2 pi by a, 4 pi by a, minus 2 pi by a, minus 4 pi by a, minus 6 pi by a, plus 6 pi by a, and so on. So this is where the real and reciprocal lattices comes into picture, and we can relate them. Now here, this line is representing the reciprocal lattice, and here we have a real space lattice. Sorry. Okay. What is the real space lattice here? Now let us forget about the detailed distribution of electron density. I mean, how is nx varying? Let's forget about this, and only keep in mind the lattice, right? So lattice doesn't tell how is your unit cell looking in detail. Lattice just says how will the unit cells be repeated. The same case here. Let us forget about the y-axis of this nx, how is nx varying with x, and only retain the x-axis. And we know that, okay, the things on y-axis will be repeating after a distance a. So we may have a lattice point here at this point, let me say 0, any lattice point here at say a. There will be another lattice point here at 2a, 4a, then to left of 0 as well at minus a, minus 2a, minus 3a, and so on, right? So this lattice in x space or real space, we can call it as a real lattice. And similarly, the corresponding lattice, which will tell you where which all terms will appear on the right hand side in the Fourier series, will give you the corresponding reciprocal lattice. So what will be the terms? One term will be at 0, another one will be at 2 pi by a, then there will be a term at minus 2 pi by a, 4 pi by a, minus 4 pi by a, and so on. So corresponding to this real space lattice, there will be a reciprocal lattice. This is a reciprocal lattice. So for one-dimensional real space lattice, where lattice points are separated by a distance a, the reciprocal lattice will be also one-dimensional lattice, and it will also be a linear arrangement of the lattice points. But the separation among the points in the reciprocal lattice will be 2 pi by a. I hope that is clear to you. So real space lattice, and reciprocal lattice are related to each other by Fourier series. The real space, and Shreya is saying I'm not audible. I don't know for how long I was not audible. Is it anyway better now? Yes, students, is it better? Could you hear me? So
Yes, sir.
was I not audible for a long time, or it was okay? I mean, it was a temporary problem.
Sir, your sound was breaking up.
Now, did you understand what I was trying to tell you or not? You missed the content, or you got the things which I wanted to tell?
Sir, I got it.
You got it. What about others? Okay. There is a issue in internet from my side. Okay, Arish got it. Okay, Shreyas want it to be repeated. Okay. So Shreya, can you help me with what you didn't get so that I can accordingly answer the questions you are confused? So did you get what is Fourier series? What is real space lattice? You understood what is real space lattice?
So I want to ask the
Me.
difference between the reciprocal lattice and the real lattice. I just, do not connect.
Sorry. I couldn't hear your voice
So
properly. You better write it in the box. Yeah, fine. Okay. The difference between reciprocal lattice and real space lattice. Okay, I'm coming to the difference. But till now, I want to know, did you get, okay, what is real space lattice? So real space lattice tells you how the lattice points are repeated in the real space, means X space in 1D case. Here we are assuming we have a one-dimensional crystal where the lattice points are repeated by a distance A. So that is, I mean, the collection of points which are repeating themselves by a separation A is called the real space lattice. Fine. Similarly, there will be corresponding reciprocal lattice, which will be telling you the terms which have to appear in the Fourier series on right hand side. And this is a lattice which is actually the lattice with periodicity of 2 pi by a. I mean, if a is the periodicity in real space, in reciprocal space the periodicity is going to be 2 pi by a. Interestingly, in if the unit of periodicity in real space is length, the unit of periodicity in reciprocal space will be inverse of the length. If the unit of periodicity in real space is time, the unit of periodicity in reciprocal space will be inverse of time. So if it is second in real space, it will be hertz in reciprocal space. If it is a meter in real space, it will be per meter in the reciprocal space. So that is also the way to try to first differentiate between the two uh, lattices. So real space lattice is inverse of reciprocal space lattice, and vice versa. So means if you have a real space lattice with periodicity A, so there will be a corresponding reciprocal lattice as well. So it is just way of representing a periodic lattice. You can represent it with the help of real space lattice, or you can equally well represent a periodic structure with the help of a reciprocal space lattice. So both are equally well. It is not like, okay, anyone is better over the other. So now it depends on our mathematical convenience, and of course the detailed nature of the uh, contents present in the unit cell in the real space lattice, that we may prefer to work in real space lattice or reciprocal space lattice. So uh, uh, theoretically, both the lattices are uh, equivalent in a sense that they can be used to represent the periodic structures. Somebody unmuted the mic and there is a huge disturbance. Please mute your mic. If anybody has to ask any question, then you unmute. Otherwise, please mute. So, anyone has to ask any question? Okay, no question. Fine. So, I hope you now are in a position to relate the two lattices. So means real space and reciprocal lattices are related to each other by Fourier series, and both are trying to represent a periodic structure. And this reciprocal now, okay, as far as we forget this information on y-axis, say for example, we just forgot how the electron density is varying within the unit cell. The details of that we ignored, and then we had only just a real space lattice and a periodic space. I mean reciprocal space lattice. So this was just these two were just periodic arrangement of points, and almost same. I mean both are infinite. In one case, the repetition is after a. In other case, the repetition is after 2 pi by a. But both are, if we forget the lengths and the units of lengths, we will say, okay, both are almost identical. Both are identical. They are just one-dimensional arrangement of periodic points. Now, when we start looking into the details of the contents in the unit cell, or how is the quantity in the unit cell varying within the unit cell, then we have to be a little careful. I mean, then the more meaning will start to appear, and now you will realize that, okay, how can a reciprocal lattice be better over a real space lattice in certain cases? Okay, now let us assume that our electron density is varying sinusoidally. It is just like a sine function having periodicity A. Now, what we are assuming is that, let us assume that the electron density is like a sine function, exactly like a sine function with the periodicity A. And within the unit cell means you have one single sine wave, correct? So, how many terms will appear in the reciprocal lattice? How many terms will appear in the reciprocal lattice? Am I audible there? Am I audible? Students? Okay, I am audible. Fine. So, I mean, how many terms will there be? in the Fourier series, if it is just like a sine function, the electron density is varying just like a sine function, exactly like a sine function. Two terms. Why two terms?
So one is the constant n naught and the other is sine.
Okay, fine. So means now if we start bothering about the detailed nature of the what you call electron distribution inside the unit cell, then number of terms which are going to appear so in the reciprocal lattice will accordingly be decided. For example, if we have only sine function with the and okay, the constant term will appear if sine function is not centered around 0 along y-axis, right? So if it is shifted along say positive x-axis, positive y-axis, we may have to add that much value to the y. That is why the constant term will be there. Otherwise, if it is centered around the y-axis, then we will be finding that constant term will be 0. So there will be only one single term in the reciprocal lattice. So if you have to represent a full sine function in real space, we have to use an infinite size plot to represent it. But in reciprocal space, we can represent it with one single term, right? And what will be the amplitude of the term? So here it is just a lattice. So when we start to define y-axis in the real space, we also have to start defining y-axis in the reciprocal space. For example, so in this case, what will be the amplitude of the term appearing in this? That we can find out from here, right? So this is how we can find out the term. So here ft will be sine of say omega naught t. Then you can find out what will be bk. Accordingly, you can find out that. Fine. I'm not going into details, but okay, you will be finding one term sitting here, like this one. Okay, whatever is the length of this term, whatever is the magnitude of the corresponding Fourier coefficient. So that will depend upon what is the amplitude of the sine function. Well, what if we have distribution of electron density like a square wave in the unit cell, and the periodicity of the square wave is say a, the same way we used to do for sine function. So suppose we have a square wave kind of distribution. So this is going like this. I hope you can follow the cursor. So it is a square wave. Then you have done it in your lower classes when you were discussing the Fourier series, that the terms will be something like there will be a term with the highest amplitude at the center. Then there will be next term with lower amplitude. Fourier coefficient will be with a lower value. Then there will be next term which is having or going to have a Fourier coefficient with further lower value, and so on. So 1 over I think k dependence is there in the Fourier coefficients for square wave, right? So what is the interesting part of working in reciprocal space is that we don't need to actually take infinite terms in the right hand side of the Fourier series. When you were discussing the Fourier series for a square wave, you tried to probably see that graph which was showing how is right hand side coming as a function of number of terms on the right hand side. So that was matching to a very good extent with the square wave, when the number of terms was something like say 100 or so. So ideally, I mean, theoretically you should take infinite terms, but practically you may be comfortable only with a few hundred terms or a few terms in the reciprocal space. So means even ideally periodically repeating structure in real space can be represented with few finite number of terms in the reciprocal space. So that is one very interesting advantage of the reciprocal space. So I don't know whether you could understand what I'm trying to say regarding the good thing of reciprocal space or not, but that's one thing. And what is the relationship between real and reciprocal space? That is Fourier series. So now, depending upon how is the shape or detailed contents of the unit cell in the real space, the contents of Fourier series, or I would say the Fourier coefficients on the right hand side, are going to be different for reciprocal space. Is it okay till now, or is there any question from the contents till now? Yes, is there any question from anyone, or is it clear? Is there any question from anyone in the class? It is clear to Harish, but about others? Only I see only 2-3 students are responding. Others are, I don't know whether they are still in front of their screen or not. Okay, fine. Let me assume that you have responded means others also are okay. If you get something, it is okay to stay silent, but if you don't get something, it is very important you should come out and ask question. Now that is where the another interesting concept of what we call Brilliant zone comes into picture. What is Brilliant zone is something like this. So you have a real space lattice, something like this, say set of points repeating after a length a. Then you have a corresponding reciprocal lattice where points are repeating after a distance 2 pi by a. Now, I hope you remember Wigner seed cell, right? So in 1D, Wigner seed cell is going to be very simple, right? How we construct Wigner seed cell or the primitive cell, we take any lattice point as the reference, then connect it to its neighboring points. So we are connecting this one with this point, and then take a perpendicular bisector. So here the length between these points is 2 pi by a. So by what length the perpendicular bisectors be passing? By pi by a, plus pi by a. Similarly, to the other side, to the left hand side, there is a lattice point sitting at a distance of minus 2 pi by a. So where is the perpendicular bisector sitting? This is sitting at minus pi by a. So this Wigner seed cell for one dimensional case, which is the smallest length unit cell. I'm saying smallest length because we are talking of 1D case. In 2D case, it will be smallest area length, smallest area cell. In 3D, it will be smallest volume unit cell, or rather the Wigner seed cell. So this is called first Brillouin zone. Fine. So how do you go to the next Brillouin zone? Is it discussed here? No. Okay. How do you go to the next second Brillouin zone? You have to connect this with the next neighbor and then draw another perpendicular bisector. And to this side as well, there will be another perpendicular bisectors here. So this region, I mean, region between pi by a and plus 2 pi by a and minus pi by a and minus 2 pi by a. These two regions constitute the second Brillouin zone, and so on. Similarly, you can have third, fourth, fifth Brillouin zone in 1D lattice. So that is the idea of the Brillouin zone, first Brillouin zone. Of course, their significance and technical relevance shall be clear over the coming classes. But yes, what is a Brillouin zone? What is the idea of the Brillouin zone? From where it is originating should be clear by now. And so now this
सर ही चले गए।
Okay, I'm sorry, there was some technical problem from my end, so I got disconnected. Now, again, coming back. Okay, here is the slideshow. Fine, so what I was talking is about Brilliant Zone. So the detailed significance of the Brilliant Zone shall be clear in the coming classes. But from where the idea of Brilliant Zones originate and what a Brilliant Zone is should be clear by now. Okay. Uh, So now, well, let's come to the idea of reciprocal lattice and try to relate real space lattice and reciprocal space lattice. And for that, rather, I would be talking about this slide, which earlier I skipped. Oh, is it the same slide? Oh, here some figure is missing. Okay, let's come here. So this is the reciprocal lattice, right? And it had a corresponding real space lattice, which I have not shown here, but I assume that it is still there in your mind, where in real space lattice the lattice points were repeating after a distance a. Here in reciprocal space, these lattice points are repeating after a distance 2 pi by a. Just like in real space lattice, we had a translation vector t, which was telling us about the periodicity of the lattice points. And what was that? Let me, okay, it's not here. Is it there in some next slides? Yeah, let me check. Yes. Okay, let's see it this way. So in real space lattice, the periodicity was, or this is what we can call the translational periodicity. In real space, periodicity was given by this function or this equation, this translation vector, where u1, u2, u3 are some integers and a1, a2, a3 are the lattice vectors in the real space. So for three-dimensional case, we will be having three lattice vectors. And what does this translation vector mean physically? Is that, okay, if you're sitting at one of the lattice points in the real space, and then you move by this translation vector, according to this rule, I mean, suppose I move by u2, u3 being 0, u1 is just 1. So it means I am going from one lattice point to its neighboring lattice point along a1 direction. So what is the meaning of this thing? Crystal is invariant under any translation given by this. Means earlier I was on one lattice point, then I moved by say 1 times a1, I moved to the next lattice point, and we have seen that in reverse lattice, what is the thing is that whenever you are on any one of the lattice points, you won't be in a position to tell whether you are you were earlier on a different lattice point or not. So I mean, the symmetry around every lattice point is identical. That is another way of saying this. So you take any translation defined by this. You take say u1 and u2 to be 1 and u3 be 0. So in that case, I'm going from say a1 plus a2, means I along one direction, say a1 direction went to one lattice point, then along a2 direction went to another lattice point, and that translation is also going to be invariant under translational operation. Means we are going to see exactly the same environment in that case. So I mean, in 3D case, this is the period, this is representing the periodicity of the lattice points. Periodicity, now you may ask, okay, we were saying periodicity is a for 1D, say for example. Okay, let me come back here. Okay, you may ask now, okay, we are saying, okay, periodicity is a in case of real space, then what do we mean by periodicity being defined by this vector, say n1 or u1, a1, u2, a2. So let us think of sine function. What is the periodicity of sine function? 2 pi. So the periodicity of sine function is not just 2 pi. 4 pi is also periodicity of the sine function, right? Similarly, 6 pi is also periodicity of the sine function. Same thing we are doing here. Means if A is the periodicity of the lattice points, 2A is also periodicity, 3A is also periodicity. Or what does this mean? Mathematically, we are saying that that our lattice is translationally invariant by all those translations defined by this equation. This is what is the meaning of this. I hope it is now clear to you. Fine. So means if you have a real space lattice, then that has a periodicity defined by T vector translational periodicity, which is say U1 A1 plus U2 A2 plus U3 A3. Similarly, if we have a three-dimensional real space lattice, then there will be a corresponding three-dimensional reciprocal space lattice. So if okay, if the reciprocal lattice, if the real space lattice was one-dimensional, what was the vectors? What was the what we will say the primitive vectors for real space? They were like n a I cap. Okay, let me again try to come to this. So if we have one-dimensional real space lattice, if we have one-dimensional real space lattice, then A2 and A3 are 0. So what is the translation vector is n or U1 into A, right? It will be like 1A, 2A, 3A, 4A, 5A means the points are repeating after these specific lengths, and there is only one direction, so we don't need to even define the direction because it is one-dimensional case. Fine. So in 1D, but if this is the translation vector, I mean n times or U1 times A1, what will be the corresponding reciprocal lattice vector for that? The reciprocal lattice vector is going to be given by this one. Okay, from here we can get what will be the lattice vector for reciprocal lattice. It will be 2 pi by A, 4 pi by A, 6 pi by A, and so on. So that is your reciprocal corresponding reciprocal space lattice vector. So we represent the reciprocal space lattice vector with the help of symbol B1. So for if A1 is the reciprocal real space lattice vector, B1 will be the if A1 is the real space lattice vector, B1 will be the reciprocal space lattice vector. And what will be the value for B1 vector in that case? If real space lattice vector is say U1 A1 I cap. Fine. So what will be the reciprocal lattice vector? That will be say N1 or V1, let us say some other integer V1 B1 I cap, right? Where B1 is equal to 2 pi by A. I hope you didn't miss my words and you understood that. Similarly, if we have a three-dimensional real space lattice, and if A1, A2, A3 are the real space lattice vectors, then what will be the corresponding reciprocal space lattice vectors? They are defined by this relation. This is nothing actually. I mean, three-dimensional reciprocal space or three-dimensional reciprocal lattice is nothing but the Fourier components, or it is representing actually the Fourier space for a three-dimensional function. So you may have Fourier series for 1D case. This is the simplest form of the Fourier series. In case you have a 3D function, then you will have three-dimensional Fourier series. One along X component, other along Y component, other along Z component. So for 1D, the reciprocal lattice is also simple. For 3D, how to construct reciprocal lattice? That can be constructed with the help of these lattice vectors. For 1D, how will we construct the lattice, reciprocal lattice? It will be constructed by the rule 2 pi by A, 4 pi by A, 6 pi by A, and so on. Rather, we can say say V1 into B1, and then for 3D, this will be following according to this rule. So in say real space, we can construct the whole lattice according to this rule. We can say, okay, let us begin with U1, U2, U3 being 0, 0, 0. So there is one lattice point. Then at 1, 0, 0, there is another lattice point after a distance A, 2, 0, 0. So this is the rule which can construct the real space lattice. What is the rule for getting the reciprocal space lattice? So these are the lattice vectors, and this is the rule. So this is the translation of the lattice points in the reciprocal space, which will construct the whole reciprocal lattice. I hope I could make it convenient to you to understand real lattice, real space lattice, and reciprocal space lattice. Still, if there are any questions, I would request you to ask it sincerely so that I can try to help you. Shreya said I was not audible. I don't know for how long. Okay, anyway, uh, if there are any questions from your end, please type your questions. I will note all your questions and will try to come up with answers in my tomorrow's class. I'm waiting for your questions. Please. Manisha didn't get it. Yes, anyone else? So I don't want to get whether I was audible or not. I just want to get your questions. What didn't you understand till now? Or what all you didn't get? Yes, please, I'm waiting so that you timely put your questions. And then I will accordingly plan my lecture for tomorrow. Okay, others? I will be talking about Boolean zones in detail in coming classes. So let's not,
B1, B2, and B3 are the primitive vector lattice.
yeah, if A1, A2, A3 are the primitive lattice vectors in the real space, then B1, B2, B3 will be primitive lattice vectors for the reciprocal space. And indeed, we have to take primitive vectors only. That will work. Yes, any other question, please? Students, please do respond whether you got it or not. Are you still confused or you got something, you understood it? At least give me some response. No questions means you understood it well. Very good. Is there anyone who still has a confusion? Please let me know, because after this I won't be going into back into the details. Then I will be getting things just as a single sentence or a term, and then we'll proceed further. So again, I'm offering you, if you still missed something, send me your questions so that I can discuss it once more if needed. Okay. B1, B2, B3 primitive vectors for yes, of course, Ankush, I answered your query. These are primitive vectors for sure. No question? All right, if there are no questions, since we are running out of time, so I can't keep on asking you for your doubts. If there are any doubts, you can approach me via email as well. But by tomorrow, by today evening, you should send me your emails, or you can also approach me via WhatsApp or whatever media you can afford, so that by today evening, you send me your questions. Till then, thank you very much. Have a nice day.